Hi, everybody. So today I'll be talking about the neocortex. All right, which is part of the brain that's dealing with reason, rational logic, and suppression. So a little bit of an overview. I'll be giving a description of what the neocortex is, talk a little bit about the current research, how that relates to pain, and then some strategies of how we can implement that into our clinical practice. So first, a quick description. The neocortex is literally the new cortex, and that's because it's the most recently evolved brain structure, and it's found only in mammals. It's a thin, six-layered neuronal mantle that covers the forebrain, and it's about 2 to 4 millimeters in humans. It's the site of all cognitive functions, from the most basic to the most abstract. And an example would be that it integrates sensory information in a dynamic manner, which is critical for perception, learning, memory, goal-directed behavior. So because it's a layer that covers across the entire surface of the brain, it has its hand, if you will, in all of the different cognitive processes. A few seminal works. Campbell in 1905 was really one of the first people to do a detailed histology of the brain, followed up by Brodmann in 1909, who was the first person to describe that neocortex as being subdivided into 6 laminae or layers. And Brodmann, he talked about it within the human brain, but he also looked at a lot of different animals. So his book really is pretty interesting because you can see kind of the differences between the animals and the human brain. Then Nieuwenhuis and Breuer in 2017 did a map of myelin content of individual architectonic areas. And then Edwards et al. In 2018 did a in vivo histology using MRI, which he shortened to HMRI. And that's super cool because a lot of our information previously was all based on cadavers. And being able to just cut into the brain after the person has passed. But this was one of the first cases where they were able to do that MRI while the person was still alive and be able to map out the histology that way. So the organization of the neocortex is, as I mentioned, that 6 layers. And this kind of gives a picture over on the side of what that looks like, and then a detail of what each one of those layers are. There's a lot of different ideas between different models for what exactly this neocortex looks like, but the one thing that is consistent across all the models is that it's that 6 layers that exists. And then the other thing is that the neuronal cell body density and size distribution within the laminae, so how many neurons and how dense it is, how thick it is between each one of those 6 layers, is not constant across all of the different regions of the brain. So there are very distinct cytoarchitectonic areas, is what they call them. Essentially, it means that depending on where you're looking in the brain, those layers are going to look differently or have different sizes. And having this sort of organization, this type of cortical structure, allows neurons to connect with each other with the minimum use of wire. So it allows these cortical areas to have all of these connections between them in a much more compact space. If we didn't have this set up like this, it would take way more volume and our heads would be way bigger. So it's pretty cool that it's set up in those layers so that there can be that communication quickly between them. Here is some images from the HMRI that I've mentioned earlier by Edwards et al. And he broke this down by macroscopic, mesoscopic, and microscopic levels and talks about what exactly what we can see on that MRI between each one of those subdivisions. So for the macroscopic, it was a parcellated area, and it's based on cytoarchitecture, myeloarchitecture, and functional specialization. So looking first at the top left image, This is the classic cytoarchitectonic parcellation from Brodmann's book in 1909. So that's how it was first described or drawn out. Then the next image down, B, is a myeloarchitectonic parcellation. Then that's compiled by Nieuwenhuis and Breuer in 2017. You'll notice that the occipital lobe on that picture is incomplete, so they're still working on it. It's not a fully completed model yet. And then the areas that are darker indicate that it's a higher myelin density, whereas the lighter areas are going to have a lower density there. So you can tell that that darkest space where it's the most densely populated with the myelin is in the primary motor and sensory areas. Next image down is C. That is a in vivo cortical parcellation based on both structural and functional MRI. And I've got a better picture of that on the next slide. Then going over into the mesoscopic scale, here's where you can see that distinct 6-layer subdivision. This is again based on cytoarchitecture and myeloarchitecture. That middle top image, or D, is just showing how it's subdivided. You can clearly see those 7 layers. I believe it's on the left is more by the cytoarchitecture, and then on the right is more by the myeloarchitecture. The next image down, E, is a post-mortem human brain, and that's a weighted MR image that shows those distinct cortical layers. And just for reference to the dotted line that's on that image is the border between the primary and secondary visual cortices. Next one down is F and G. So this shows, they call them functional cortical columns. So essentially we know that we have those 6 layers in the brain that covers across the whole brain. And then those 6 layers make up columns, and those columns are functional columns. So they each have their own specific purpose. So the one on the left, or F, that is the functional cortical column for ocular dominance. And then on the right, G, is the functional cortical column for orientational preference in the human visual cortex. The microscale is all about neuronal cell bodies, myelinated fibers, and glial cells. I'm not going to get too far into that. That's a bit beyond the scope of what we really need to be discussing in this presentation. But just a quick reference of what those images are. H is a fluorescent microscopy. It's of the human cortex from the temporal lobe that shows the neuronal cell bodies in green, the myelinated fibers in red, and then astroglia in blue. And then the next image down, I, is the electron microscopy of the myelin sheath around axonal fibers, and that's another postmortem image. And then the last image down there, J, is iron localized within the oligodendrocytes and the myelinated fibers, which contributes to MRI contrast. So interesting stuff, just a bit beyond how deep we need to be getting in this presentation. As I mentioned, this is that combination of structural and it's the structural and the functional MRI. So this is a map of the brain and where that parts of the brain gets highlighted with different functions or tasks of the neocortex. So you have the auditory section, sensory motor, visual, and this shows us all of some of the different cognitive functions that neocortex is involved with as well. So how does the neocortex works? There are bidirectional, short and long-range connections between neuronal networks that belong to different cortical areas. They exert distinct cognitive functions that are then dependent on specific regional specifications. A lot of words there. Essentially, there's, just to kind of break it down, there's these neuron subtypes that interact together. And then together, those make up these cortical networks. And those cortical networks have their own connective properties. They create different brain states. And then that's what results in our cognitive processes. And that will be things like visual, auditory, associative, all of those things. So each cortical network harbors several subnetworks or cortical layers and microcircuits. And these basic units of neural computation are what we call cognition. Again, this gets pretty deep, but I'm not going to go too far into this. However, it's kind of an important stepping stone for the next pieces. So in order to encode the information that is received, there's two different schemes, the rate coding and the temporal coding. Rate coding is more about sensory patterns, and it is where there's a specific external stimulus that conveys that information to the recipient neuron. And then there's different variations in the spike rate, and that's how that's read. And it's over a relatively large time window. The temporal coding is what we're going to focus on a little bit more here today, and that's where relevant information resides in very precise temporal occurrence of a single action potential within a train. So within this, there are a group of action potentials that are all fired within a very short time window, and so it behaves as one cognitive functional unit. So then that brings us forward to temporal coordination. And you can almost think of this as a orchestra conductor. So there are cortical networks that do require that like very precise temporal coordination in order to reach computational complexity. So you'll have excitation and inhibition that are both being balanced and fine-tuned. So you have the onset and the offset, which have rate-varying spike trains that will relieve and then reestablish some of those inhibitory tones, and then that creates a very specific pattern. So essentially, both that excitation and inhibition are key components to this, and you need both in order to have very specific patterns. And that's where, that orchestra conductor comes in, bringing and flowing, ebbing and flowing. And then down that train a little bit further is our GABAergic neurons, and these are some of those inhibitory neurons that project from the neocortex. So we know that both excitation and inhibition is important, and then in talking about pain, this GABAergic is a little more discussed, and so this inhibition piece is what we want to focus on. It does have a significant contribution to brain computational power. So things like learning and memory, anxiety, sleep, and cognition. These GABAergic neurons are important to prevent runaway excitation. So again, to bring things back down. And then if there are any abnormalities within this, then that can lead to neurological and psychiatric disease. So that's where we think that Alzheimer's and schizophrenia and some of those other diseases are coming from. And there's a couple of main classes. The parvalbumin and the somatostatin are the ones that are probably most discussed in the literature, but I'm not going to go too heavy into detail on that one. This is just to kind of give you a picture of how those GABAergic circuits work. So this is all pretty new within the literature. There's a lot we don't know yet. As you can see, it's a very complex system, but there is some work being done in the literature with disinhibition in the spinal cord to relieve chronic pain, especially things like nerve injury-induced mechanical allodynia, and then also just modulating neuronal activity in cortical and subcortical areas that are involved in both the sensory and affective components of pain. So we know, essentially this is saying that we know that these GABAergic circuits are important for the pain experience. We know that if we can work within those circuits or modulate those circuits, then it could potentially have useful effects on pain, and it's a relatively new area within the literature. So hopefully we'll see a bit more coming out of that in the next couple of years. So now we're going to slide gears a little bit into how can we use all of this information? Why does it matter to us in the athletic training room in day-to-day practice? So some strategies that kind of involve using that neocortex for modulating pain would be looking at things like attention and then mood and affective state. There are a couple studies that show that modulating attention can change perceived pain intensity, whereas a change in mood or affective state can modulate the unpleasantness of pain. So two different aspects of pain that we can reach, but depending on what exactly we're hitting. Some examples that have been used within these studies are doing things like mathematical tasks. So that's that attention piece. There's also a lot of research on using films, music, images, and odors in order to change the more of the mood side or the pleasant, unpleasantness of pain. So those are saying that a positive mood induces stimuli that attenuates pain, whereas a negative mood could potentially increase pain. And another really interesting idea working within this neocortex would be the using vagal nerve stimulation. So vagal nerve stimulation is already an FDA-approved therapy for treatment-resistant depression. So it's already being used for that mood and affective component. Vagal tone can be assessed by measuring heart rate variability. So this is a way of being able to determine if we're actually doing anything with our treatments or not to that vagal tone. So poor vagal parasympathetic tone results in decreased heart rate variability, and it's associated with a wide range of poor health conditions. So we want that increased parasympathetic tone and increased heart rate variability. So vagal nerve stimulation works by activating the locus coeruleus, which is going to release norepinephrine, and then the raphe nuclei, which is going to release serotonin. We've talked about these descending pain pathways a little bit in previous presentations. So just referring back to some of those pathways. And then it also, by activating that, it modulates pain perception and psychological states and processes. And then the other piece where it's connected into that neocortex is it modulates inhibitory control processes. So there's that GABA pathway coming back, and that's how that connects there. So within that vagal nerve stimulation, some of the research that's been done within this field, there are a couple main outcomes that they've looked at, and this specifically has been with, or the ones that I've reported here are after transcutaneous vagal nerve stimulation. So that's where they put electrodes on the ears and stimulate the vagal nerve that way. So some of their outcomes have been on affect, which they've seen decreased depression and anxiety. On pain, they've seen increased bone and muscle pain threshold and decreased migraine pain. So a lot of the studies have been on migraine and headache literature. And then cognition, there's enhanced memory performances and increased reaction time and response selection during action cascading. A couple of the methods that are typically seen within the literature regarding vagal nerve stimulation are electrical VNS with an implantable device. So that is a invasive treatment, if you will. And then there's more that transcutaneous, where it's that superficial surface level vagal nerve stimulator. And then kind of within that, a sub-branch would be stimulating the auricular branch of the vagus nerve. So that's dealing with that ear, like those ear electrodes. Kind of an interesting story. When I had my wisdom teeth out, actually, I didn't have a lot of time. So rather than having them schedule me for a couple weeks out where they would put me under general anesthesia, I opted to just do it local anesthesia. And so at that point, they were testing those auricular vagus nerve stimulation devices for pain. So they actually clipped little electrodes onto my ears, and I sat with that on there for a bit first, and then they went in, and they did the local analgesic as well, and then they went in and took my wisdom teeth out. I wish it were a great experience for me personally, but it made me really nauseous, so that was less fun. So hopefully they've kind of figured that out a bit more since then. That was back in 2018. So hopefully they've come a little bit further on that one. Some other methods would be administration of acetylcholine or its derivatives. The thing with all of those methods is obviously we won't be doing those in the athletic training room unless we are at a place with a lot of money or research, really research heavy and has access to a lot of those cool things. However, there are some natural methods to get that vagal nerve stimulation using things like nutrition, exercise, and psychological stress. So first, paced breathing. I wanted to give this one its own slide, its own moment, because this is something that we talked a lot about over the summer while we were all there in Idaho. And so I'm not going to go back and recover all of those techniques that we learned on how to work with breathing, but those would all be really great options. And there is a study that was looking at slow, deep breathing. And they found that all of the methods that they tried did have a increase in the parasympathetic nervous system. It was most effective whenever they were able to reach 6 breaths per minute with a 1-to-1, or that's one inhalation to one exhalation ratio. However, the most lasting impact was whenever they were able to guide the patient to lower their rate to that 6 breaths per minute. So rather than just counting off and telling them you're doing this, you guide them into it. So you help their system adjust into it. And then with a 1-to-2, so inhalation to exhalation ratio. And then some other options that we can use or suggest within our practice would be either we can do guided breathing, or teach them the box breathing technique. Or there's a lot of deep breathing phone or watch applications. I know like the Apple Watch has the breathing meditation that guides you through it for 2 minutes. And there's a lot of options for that, just different applications on phones as well. So for reducing psychological stress, super interesting study having to do with chanting and how that can actually stimulate the auricular branch. So that ear branch of the vagus nerve is the theory of how this works. But Kalyani et al. In 2011 did chanting while doing an fMRI, and it produced significant bilateral deactivation of the brain in several different areas. And they compared it to a sham and compared it, I believe, and to like S's, and the other two groups didn't have that same deactivation. So it has to be that specifically. Some other methods are music therapy, which is shown to increase parasympathetic activity, mindfulness practice, practicing forgiveness. So in that study, they had taken a group, and the participants in the forgiveness group just had to think about what would it be like if I were to forgive this transgression, versus another group that didn't forgive or leaned into it, versus a third group that just distracted themselves completely. And then the greatest heart rate variability increase was that group that had that thought process of what would it be like if I were to forgive. So pretty cool stuff there. And then also laughter. They aren't kidding when they say that it's good for the soul. It's also good for the heart and the parasympathetic nervous system. Exercise. So aerobic exercise is going to increase gastric motility and vagal tone. Things like stretching, resistance training, yoga, these are all well-studied things, things that we talk about a lot within the athletic training clinics. So it's good just to reinforce that. Nutrition, things like omega-3 fatty acids, or even just eating fish, can have beneficial effects on heart rate variability and the parasympathetic activity. Probiotics can stimulate vagal afferents to the brain. So the theory is that the gut microbiome can affect human brain health. And there was an animal study done where they found a specific bacteria that was shown to cause neurochemical changes in the brain. So cool stuff there. Curious to see what else comes out of that as they kind of move that more into studies with humans. And then fasting, so intermittent fasting, different types there will also increase your heart rate variability. then I found some other just kind of interesting or more alternative methods that are theorized to or have some seen some effects in vagus nerve stimulation, things like massage that increase heart rate variability and vagal tone. And those different types of massage that I listed were just what was used within the study. So I'm sure other types do as well, but those are the only ones that we can report on because those were the ones that were used in that particular study. Even a gag reflex can stimulate the vagus nerve. So an example would be like a tongue scraper or a cleaner for during oral hygiene while you're brushing your teeth. Essentially, it increases that heart rate and then calms back down and settles, so it's increasing that variability. Cold water facial immersion has a greater reactivation of parasympathetic system. So in that 50 to 60 degrees Fahrenheit following exercise. So essentially, if an athlete or a patient is wanting to hop in the cold tub, you can tell them to just go ahead and dunk their face below real quick too, and then that way they get some parasympathetic effects as well. But also acclimation to the cold is said to increase parasympathetic tone. So great for people in colder environments. And then the other one that I thought was interesting was sleeping on the right side. So lying supine just on your back had the lowest increase in parasympathetic tone. And then the highest was that right lateral decubitus position, so laying on the right side. The implications, or almost more of a summary here, the neocortex is involved in all cognitive functions. It covers across the entire brain in different layers. And then there are benefits on pain perception if we can modulate attention and mood and affective states, potentially through some of that GABA inhibition tract, which is also useful for that vagal nerve stimulation. So neocortex has its hand in a lot of different things. So if we can modulate or change some of those things, that can have positive effects on pain. And that vagal nerve stimulation we can get through psychological stress or different psychological techniques, exercise, nutrition, and a variety of alternative methods. Those are all things that we can talk about or do or educate within our athletic training rooms. That is my references. And I look forward to hearing you all's questions for me on Monday. Thanks, guys. If I can figure out how to turn this off. Okay, thanks, guys.